Okay, everyone, welcome back. In this video, we're going to continue our discussions on stereochemical aspects of the E2 reaction. In the previous video, we saw that E2 reactions are stereoselective. So when there are two beta hydrogens on a beta carbon, then the reaction selects one product over the other product. So in that particular case, it was cis arrow trans. Okay, what we're going to do here is we're going to look at substrates which have only one beta hydrogen on a beta carbon. Okay, there's only one beta hydrogen on a beta carbon, and let's see what can we learn from this scenario. So to start, what we'll do is we'll look at an example, and I'm picking this example from the textbook, but you can work out other problems and see what happens. So let's say we have a substrate, that's this molecule. There's some metal over there. And then we have hydrogen, and there's tert-butyl. So this is our substrate that we have. And the reaction, what we're doing is we're going to react this with NaOET, let's say, in ethanol with heat. That's the reaction. Again, E2 reaction. So we're trying to write an elimination product here. So when we look at this substrate, that's the halogen, which means this is our alpha carbon, okay? And now any carbon that's connected to alpha is a beta carbon. So notice how this carbon is beta, but that beta carbon does not have any hydrogens to it because it's connected to 3 methyl groups and then that carbon. So there are no beta hydrogens over there. The other beta carbon we have is here. Let's call it beta prime. In fact, what we can do is, since there are no hydrogens on that beta carbon, we can just ignore that carbon. And let's say this is our beta carbon. And now on this beta carbon, we only have one beta hydrogen. This is the only beta hydrogen that we have. So let's see what product we get in this particular case. So we'll come back and fill that product, you know, what the structure of the product is in a bit after we work through the mechanism of the reaction. Now, mechanistically, remember that what we have to do is we need the H beta and the bromine to be anti-periplanar to each other or anti to each other. So what we're going to do is we're going to draw a Newman projection about this alpha beta bond. Now, you don't have to look from here. You can look at it from there. Either way, it doesn't matter. That's not going to change the outcome per se. Okay, but I'm just looking at from here. So when I look at the beta carbon from here, on the beta carbon, I see a hydrogen pointing down. Okay, it's in the plane of the board. There is a pH. The pH stands for a phenyl ring. Okay, so pH is basically a benzene ring. This is what pH stands for, a phenyl ring. So we have a phenyl to our right and methyl to our left. And this is actually our H beta. On the back carbon, which is the alpha carbon, we have bromine pointing up. We have bromine pointing straight up. And then to the right, is a hydrogen, and to the left is this third butyl group. Okay, so that's my Newman projection. And what you should notice is once we draw this Newman projection out, we actually have H beta and the halogen anti to each other. That is what we want. Okay, these are anti to each other. So that means our base, which is the ethoxide, this can actually go ahead and deprotonate H beta. Those electrons would go into the space between alpha and beta, and Br would get kicked out. And this Newman projection tells us how the groups are oriented. So we have beta carbon, which is the front carbon, okay? So this is beta, and then the back carbon is alpha. So we have the double bond is formed between beta and alpha. So on the beta carbon, you can notice that there is a methyl group. Okay, so the methyl group is on the beta carbon, and this third butyl group is on the alpha carbon, and the methyl and the third butyl group are on the same side of this plane, the plane where the H and the Br were. So that means on the alpha carbon, the third butyl group is there. And then on the beta carbon, the phenyl group is on the right side. So it doesn't matter whether how you draw it. So phenyl group here, on one side there is a phenyl group, and the hydrogen on the alpha carbon is on the same side. So we can draw the hydrogen here. So we get this product, okay? And so that is the product that we get. That should be our product. Now, there is no other beta hydrogen here, so we will not get any other product. So that's the only product that we are going to get. Okay, so that means our product in this particular case is going to be this molecule. Let me draw this out. And again, I want you guys to work through assigning ENZ configurations. This is an E alkene. Okay, that's an E alkene. So that's an E alkene. Now what we're going to do is we're actually going to go ahead and assign configuration to this alkyl halide that we started with. Okay, let's go ahead and assign configuration to this alkyl halide. So for the alpha carbon, the highest priority group is the bromine. The lowest priority group is the hydrogen. And then we have this carbon here, which is connected to 3 carbon atoms. And we have this carbon here, the beta carbon, which is connected to 1 hydrogen and 2 other carbon atoms. So that means this gets a higher priority. So we're basically going one, 2, and 3 like that. So in going from 1 to 2 to 3, this is a clockwise rotation, but the lowest priority group is pointing towards us. So that means this is an S stereocenter. Okay, that chiral center is of the S configuration. Now for the for the other chiral center, which is the beta carbon, we have the beta carbon is connected to 3 carbon atoms. And then that carbon has a bromine attached to it. So that's going to get 1. And then this is 2. And this is 3. And in going from 1 to 2 to 3, I'm actually looking at the molecule. You might want to try this out, but I'm looking at the molecule. Well, it's fine. Let's just do it this way. 1, 2, 3. This is counterclockwise with the H beta pointing towards us. So this is an R configuration. 1, 2, 3 counterclockwise, but H beta towards us. So this is R configuration. So that's the configuration of the two chiral centers in our starting material. Why did we do this? I want to show you something. So what we're going to do is we're going to change our alkyl halide a little bit, okay? And we're going to draw another molecule where, say, the phenyl is here. The methyl is here. And the hydrogen is here. Wait, no. That's not what we want to do. No, I want to keep the hydrogen in the same place and swap the methyl and the phenyl. Okay, so now for this new alkyl halide that we've drawn, let's go ahead and assign configurations right away. The first chiral center here is identical to the top molecule. Nothing changed about it. That means this chiral center is of the S configuration still. Okay, they're the same. They're identical. For the second chiral center here, what we did is we swapped two groups. So what should that do to the configuration? This was R, and that means this is S over here. Okay, so they're both S. How are these molecules related to each other? Okay, they are diastereomers of each other. Okay, they're two diastereomers of each other. Okay, we're going to do the same reaction on this molecule. And again, for doing this, we'll have to draw the Newman projection. So we're going to first go ahead and draw the Newman projection. So when I look at the, not alpha, beta, and alpha, and we're looking at in this direction. When I look at that beta carbon, I see hydrogen going down, methyl going to the right now, phenyl going to the left. On the back carbon, we see bromine going up, third butyl going to the left, and hydrogen going to the right. And sorry, this is our H beta, this is our H beta. So the bromine and the H beta are anti to each other. If they were not anti to each other, then we would rotate the molecule. We will do as we rotate in a Newman projection to put them anti to each other if they were not anti to each other. So that's key. That's the stereochemical requirement for an E2 reaction, that they have to be anti to each other. So now we have those anti. So what can happen is that our base here, the OET, this can come and deprotonate. Electrons go here, the bromine gets kicked out. And so what we would get as our product now, if you notice, at the beta carbon, which is our front carbon, the beta carbon and alpha carbon, if you notice, phenyl on the beta carbon and third butyl on the alpha carbon are on the same side. So phenyl and third butyl are on the same side, and methyl on the beta carbon and hydrogen on the alpha carbon on the same side. So methyl on beta, hydrogen or alpha, they're on the same side. Okay, so that would be our product. And this product here is Z. Okay, that's Z. And there is no other alkene product that we are going to make here. We will only get the Z product. Okay, so because of this, what we say is that E2 reaction is stereospecific. Also, because what happens in a stereospecific reaction is one stereoisomer of the reactant is going to give you one stereoisomer of the product. Okay, so if you start with a specific stereoisomer of the reactant, you're going to get a specific stereoisomer of the product. If you start with another stereoisomer of the reactant, you're going to get another stereoisomer of the product. And that's exactly what we're seeing here. We started with one diastereomer of the reactant, which was R, and we got the E alkene. We started with the SS diastereomer and we got Z alkene. So you notice how one stereoisomer gives us one stereoisomeric product. One stereoisomer gives the other stereoisomer gives us the other stereoisomer product. They do not cross. There is no way that this diastereomer here, RS of the alkyl halide, would give us the Z alkene. That's not going to happen. Or this one giving us the E alkene. That does not happen. So because one stereoisomer of the reactant gives a specific stereoisomer of the product, okay, or as a specific stereoisomer of the product. They will never cross. So we say E2 reactions are stereospecific also. So E2 is stereoselective, and it is stereospecific, and it is regioselective. So there are several attributes to an E2 reaction. And all of this is possible because it is a concerted process. Everything happens in one step. So when you do something like in a concerted way, when a reaction happens in a concerted way, then there is a lot of control that's possible in the reaction. But if a reaction happens in several steps, when you make intermediates, then the control is lost to some extent. You can still control those, okay? You can still control those by focusing on your rate determining step and things like that. But a greater degree of control is possible when you do things in one step, because everything has to be done precisely in a way, okay? You can control it otherwise also, but it's harder, okay? With the concerted processes, the control is very easy. Okay, so this was simple alkyl halides. How does this extend to cyclohexanes? Because those are the other molecules that we've seen, okay? Which is now basically an extension of this, okay? In cyclohexanes, the stereochemical requirement in E2 reactions. In fact, maybe I should say, what is the stereochemical requirement? Okay, this is stereochemical requirement is the anti-periplanar arrangement, okay, in E2 reactions translates to trans diaxial arrangement of H beta and the halogen. Okay, so when we're looking at simple chain alkyl halides, long chain alkyl halides, aliphatic alkyl halides, then we needed an anti-periplanar requirement. The same thing when you talk about cyclohexane, it becomes a trans diaxial arrangement between H beta and the halogen. Okay, and so what that means is, so for an example like this, if we have a cyclohexane, and let's say we have a bromine over there, and there is a methyl group here, and there's a methyl group here. And what we're going to do is we are talking about an E2 reaction. So let's just say this is NaOCH3 with methanol and heat. Okay, that's the E2 reaction that we're talking about. So this is our alkyl halide. This is alpha. That means we have beta and we have beta prime. So we have two possible beta carbons here. Okay. Now the requirement in cyclohexanes is that H beta and the halogen, they have to be trans diaxial. Now they can be diaxial, but the important thing is they must be trans. So if you look at beta carbon, the beta carbon, there is a hydrogen here, but that hydrogen is cis to the halogen. That means we cannot get it trans because they're always going to be cis. You can draw chairs and everything, but you cannot change the stereochemical relationship. If two groups are cis, then they're going to remain cis, whether you draw it like this in 2D or you draw a chair which is more like three-dimensional. Okay, so that's never going to happen. Now in beta prime, there is a hydrogen which is on a wedge. Okay, so this is a methyl group. Again, to remove any confusion, that's a methyl group, this is a methyl group. So what you notice is H beta prime, and this is H beta, that is cis, but H beta prime and the bromine, these are trans to each other. The bromine is on a dash, H beta prime is on a wedge. That means when we do this E2 reaction, the reaction's only going to happen here. Although there is another beta hydrogen, the reaction only happens over here. And so our product from this reaction is going to be methyl. That doesn't change. This was the beta carbon. Everything remains the same over there. So the methoxide is going to come and get H beta prime. That, or let me use dotted arrows because there are too many arrows right now. I don't want that to be confusion. So this is going to come and get H beta. Those electrons drop into the space between alpha and beta, and the Br gets kicked out. Okay, so E2, and so what we're going to get is a double bond between alpha and beta, and since this alpha and beta prime, and now since beta prime carbon is sp2 hybridized, this methyl group is not going to be on a dash. It is basically a straight line. So that will be our product. H beta is still there. Nothing would happen to that. So that's the outcome of E2 reaction, the stereochemical requirements that are imposed by an E2 reaction. So in cyclohexanes, what it means is any H beta that is trans to our halogen, those are the only ones that can be deprotonated, and they would result in products. Okay, so hopefully all of this was helpful. I know there's a lot of there are a lot of aspects to it, so please practice all the problems. Definitely practice some of the in-chapter problems so that you see these as you do things. You know, as you learn a concept, you're actually able to apply it. You know, that's very important. So keep practicing. So after this, we're going to go into substitution and elimination, but we'll talk about SN1 and SN1 and E1 reactions. Okay, so we'll talk about those in the next video.